Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. My name is Kaisar Habib and today I am going to present one of our research project titled as Internet of Things IoT Enhanced Educational Toolkit for Teaching and Learning of Science, Technology, Engineering and Mathematics STEM. In this project, my other team members are Mr. Elson A. Tenkai, my honorable supervisor and team leader, Associate Professor Dr. Mohammad Hanif bin Saad, my honorable co-supervisor, Professor Dr. Aini Hussain, Dr. Afida Ayub, and Mr. Ammar Shafiq Zubahul Ahmed. As we know, investment of the Internet of Things IoT fortifies intelligent system development for heterogeneous information management in various aspects. IoT is a buzzword towards automation, integration, and information exchange that brings technological transformation and impacted almost every domain over the world. In such avenue, information produced from STEM fields also can be successfully integrated with the help of IoT to achieve competency with the global technology through supplying skilled personnel equipped with such IoT-based STEM knowledge. According to the World Economic Forum, it is expected that 65% of kids in primary education will end up working in jobs that have not been created yet. Besides, only 44% of school students enroll in the STEM field in the year of 2018 compared to 48% in the year of 2012. Furthermore, in Malaysia, the number of students taking science subjects at the STPM level has been declining from 5,475 students in the year of 2017 to 4,566 students in 2018. According to Academy Science Malaysia ASM, parents are one of the contributing factors to this decline who influence their children to involve in literature or economic subjects for getting excellent grades in the SPM examination. A recent survey by the Ministry of Science, Technology and Innovation (MOSTI) stated that nearly 70% of students voiced their unwillingness to acquire knowledge in the STEM subjects due to the lack of practical teaching. Several initiatives have already been introduced by the Malaysian government to give students more exposure on STEM education and cultivate their interest of younger generation towards STEM discipline and inspire them in choosing a career in this field. For instance, the ESTECC education program by the Ministry of Energy, Science, Technology, Environment and Climate Change Malaysia, also STEM for All from the Ministry of Education Malaysia in collaboration with Microsoft Malaysia. However, it is noticed that theory-based teaching and learning system declining students' interest in the STEM education. Thus, the number of people who will venture into STEM will decline if further no steps for interventions are implemented. To alleviate this issue, project-based learning (PBL) can cultivate the interest of the younger generation towards the STEM discipline. The project-based learning promotes constructing knowledge through meaningful projects and real-world products. It exposes the students to the problems in their surroundings while encouraging execute tasks in collaborative manner among the individuals. The project-based learning provides an opportunity for engagement with the context explored by all the four STEM fields through challenging the students with real-world problems and asking them to innovate a unique solution. This situation could prepare them for the future workplace where communication, innovation, and collaboration are essential to ensure long-term solutions. The project-based learning scheme lacks in the involvement of IoT technologies for development, testing, and taking necessary modification of the design project. Cloud Paradigm might be the pioneer choice in this aspect that enables IoT-fortified data flow over the internet. After an extensive literature review and case studies, it is identified that the current teaching and learning systems are lacking in Smart Learning Toolkit to equip the students with the IoT-based science, technology, engineering, and mathematics STEM knowledge learning. The fundamental objective of this study is to develop a low-cost smart toolkit for small-scale analog and digital data acquisition, output production, and perform wireless data transfer for exposing science, technology, engineering, and mathematics knowledge to the students. Besides, a teaching and learning module based on this developed smart toolkit has been designed that prioritizes project-based learning approach for cloud-facilitated STEM education instead of conventional theory-based learning. This IoT-based PBL approach can be utilized in exposing students to STEM through a cloud-facilitated Raspberry Pi-based toolkit and might be a contributing factor to instill the interest in STEM knowledge-related technologies in the younger generations. The hardware utilized in this research includes an input-output test board as the end user field device to generate input test signals or represent output signals in both analog and digital form, an analog to digital converter to make the input-output signal compatible with microcontroller and microprocessors, a Raspberry Pi 3 Model B Plus as the main controller toolkit of the proposed system to perform input-output signal processing and transfer acquisition data to the cloud platform through HTTP request, and Think Central Cloud Platform to receive the Raspberry Pi toolkit, transferred HTTP request, parse data from the request and store in a dedicated MariaDB database. The input-output test board that is used to generate the input test signals or represent output signals in both analog and digital form is equipped with 8 light-emitting diodes to represent the digital signals received from the toolkit during the digital output data production phase, 1 voltmeter to display analog voltage level received from the toolkit during the analog output data production phase. This testboard also comprises of 8 toggle switches to generate and provide 8 discrete signals to the Raspberry Pi toolkit as the digital input signal, and 1 potentiometer of 0 to 10 kilo ohm range to provide 0 to 5 volt analog voltage to the Raspberry Pi toolkit as the analog input signal. The image shows the testboard used in this research. The analog to digital converter constitutes of ADC0804 IC, whose reference voltage pin is responsible for generate voltage as 8-bit discrete manner and provide to the Raspberry Pi toolkit to perform analog input voltage acquisition. The resolution of this 8-bit ADC for the 0 to 5 volt input voltage span is shown in equation 1. This equation indicates that the ADC output will change by 1 unit for each 19.5 mV change of the ADC input voltage. Besides, Raspberry Pi GPIO pins are designed to deal with 3.3 volt at 16 mA current for each. For the analog output data production phase, the allowed voltage span size produced from the toolkit slider control as shown in equation 2 is 0.0339 step size was found from this equation for the highest 100 step level of the toolkit controller application slider control within 0 to 3.3 volt. Raspberry Pi Model B Plus is a lightweight credit card sized small Linux computer that comes with Broadcom BCM2837 Cortex A53 quad-core processor. Data transfer rate of this ARM processor is 64-bit, having a clock frequency of 1.4 GHz with 1 GB LPDDR2 RAM. Raspberry Pi is equipped with 40 onboard 2.54mm general-purpose input-output GPIO header pins that supports serial universal asynchronous receiver transmitter UART, inter-integrated circuit I2C, and pulse width modulation PWM communication scheme to interface with the external hardware. Besides, it exhibits PCM 43438 wireless dual band 2.4 or 5 GHz Wi-Fi driver for the internet connectivity. Facilitating these features, Raspberry Pi is the heart of this project that involves in hosting the Toolkit controller application to provide GUI-based application support, input signal acquisition from the IoT board, signal duplication, trimming and processing, output signal generation to the IoT board, transfers data to the Things Central cloud. Several services currently exist that provides platform as a service-based cloud to develop IoT-based STEM applications. However, these platforms exhibit either license or subscription-based schemes through their system. In this study, we involved Think Central Cloud Platform to support wireless data management transfer from the Toolkit controller application to facilitate the project-based STEM teaching and learning scheme. Think Central is a cost-effective IoT-based cloud platform to rapidly develop and deploy IoT applications without concerning on the subscription, storage, and computation infrastructures. Table 1 enlisted the basic specification of Think Central Cloud Platform. Table 1 enlisted the basic specifications of Think Central Cloud Platform. Think Central is a standalone server-client architecture-based web service that deployed in a Apache 2 web server with dedicated publicly accessible web address. It involved a RESTful API to handle HTTP GET-based web requests, parse data from the received request, and structurally store this received data in the dedicated MariaDB database. Think Central Platform also offers to display this stored data in a customized dashboard through 11 widget modules for further analysis and decision making. Think Central also allows creating a customizable project dashboard through these widgets to represent data in different graphical and statistical forms. This customized project dashboard can be set either public to access by the individuals, or private that is intended to access for that user only. The research execution was categorized into 4 different phases: the development phase, the preparation phase, the data processing phase, and the data transfer phase. The development phase involved making connections between the Raspberry Pi ADC circuit and the input-output testboard. A controller application was deployed in the Raspberry Pi toolkit, which front-end user interface allows taking user commands through GUI controls. Also, a Python-based backend script was integrated with the controller applications to deal with the GPIO pins for analog or digital input signal acquisition and output signal production. The preparation phase involves configuring the Think Central Cloud Platform by creating a user account for authorized data transfer and preparing the desired number of sensor credentials to allocate toolkit transfer data. This user ID is a unique credential obtained while creating a user account, where the sensor ID is the data identity involved in storing and retrieval of specific data from the database. Think Central allows creating several projects under the authorized user credentials that exhibits authentication, encryption, and security for data management with the database server. Figure 1 shows the overall system architecture and data flow diagram from input data acquisition to the cloud-based data representation. In the data processing phase, the input-output testboard generates analog or digital test signals and made compatible with the Raspberry Pi through the ADC circuit. These signals fed to the Raspberry Pi toolkit through dedicated GPIO pins to convey the input-output data acquisition phenomenon. The toolkit controller application performs data processing tasks, updates the controller GUI, and transfers this acquisition data to the Think Central Cloud Platform. The toolkit controller application also generates digital or variable duty cycle based pulse width modulation signals and passes them to the input-output testboard through the dedicated GPIO pins to perform output data presentation. The last data transfer phase aims to transfer digital and analog input acquisition data to the Think Central Cloud Platform. The controller application front-end script incorporated with a socket class to transfer data through HTTP GET web request. A static token is used for secure data communication with the header segment of each HTTP request. These requests are concatenated with user ID followed by sensor ID and in conjunction with the sensor value. The sensor value segment contains 1 for high and 0 for low signal obtained during the digital input data acquisition and the numerical value obtained during the analog input data acquisition from the GPIO pins. Think Central Cloud Platform structurally store data in a dedicated database table and represent data graphically for testing, validation, and performance evaluation. The input-output test board was powered by a single-phase 220 voltage supply, and the Raspberry Pi Toolkit was powered by a 220 to 5 volt DC 2.5 ampere adapter module. The connection scheme for digital input acquisition and output production by the Toolkit application through the input-output test board is shown in figure 2.A. For the sake of simplicity, the schematic depicted only one input-output test board toggle switch as discrete input and one input-output test board LED as discrete output presentation, wired with two dedicated individual GPIO pins. One end of all the input-output test board toggle switches was connected with the Pi 3.3 volt to make or break this DC voltage signal during the digital input signal acquisition. The remaining end of these toggle switches was connected with the dedicated Pi GPIO pins to sense the corresponding input signal level and realize the input-output test board switching status by the controller application. For digital output signal production, one end of all the input-output test board LEDs were connected with the Pi ground terminal through a 330 ohm resistor for each, where the corresponding remaining end of this LED was connected with the Pi dedicated GPIO pins. This phenomena illustrates digital output signal generation by the Toolkit controller application in the GPIO pins and presents this GPIO pin status through the corresponding LED of the input-output test board. Besides, the connection configuration between the Pi and input-output test board for digital input signal acquisition and output production is mentioned in Table 2, where the connection configuration for analog input acquisition and output production is listed in Table 3. For the analog signal acquisition, the input-output test board 0 to 10 kilo ohm potentiometers output and was connected with the positive biasing pin of the ADC 0804 analog to digital converter IC. The reference voltage pin of this ADC was connected with the Pi GPIO pin. This scheme illustrates generating variable voltage by the input-output test board potentiometer, making the voltage compatible with the Raspberry Pi through ADC and providing the generated voltage in the Pi GPIO pin to realize the voltage and update corresponding GUI controls by the Toolkit controller. Moreover, for investigating the analog output signal production, variable pulse width modulation signal produced by the controller application through varying the signal conduction state duty cycle was applied to the voltmeter through Pi GPIO pin 7. This phenomenon represents variable 0 to 3.3 volt output voltage production by the toolkit and display the corresponding voltage level through the input-output test board voltmeter. The experiments on the proposed system was conveyed to investigate analog input data acquisition AIDA, analog output data production AODP, digital input data acquisition DIDA, and digital output data production DODP. Besides, the network capabilities were unlocked by Raspberry Pi dual band Wi-Fi driver and HTTP socket class to transfer event status to the Think Central platform. These data were gathered into a database and able to retype from the Think Central graphical user interface. As for the digital input data acquisition, toggling the input-output test board switches produced either logic low for turn-off or logic high level for the turn-on states. These discrete signals then passed to the Raspberry Pi toolkit through dedicated GPIO pins The changes in GPIO were realized by the Toolkit controller script and will update corresponding digital input switching status based on the GPIO status obtained. The Raspberry Pi Toolkit controller application transfers this digital acquisition data to the ThinkCenter cloud platform through HTTP web request. Upon getting access to the ThinkCentral cloud platform through its dedicated web address, user need to browse the sensor data page and need to provide valid project, location, gateway, and sensor ID to investigate the desired sensor credentials. The video clip demonstrates both graphical and statistical investigation of the last 20 stored data of each input-output dashboard switch from the sensor data page of ThinkCentral Web Service graphical user interface. For the digital output data production, clicking a toggle switch control in the Toolkit controller graphical user interface will produces logic low signal for the switch is in off state or generates logic high signal for the switch is in on state. This discrete logic low or logic high signals then feed to the corresponding GPIO pins. The input-output dashboard green LED will be turned on for this logic high or turned off for the logic low signal received from the associated connected Raspberry Pi Toolkit GPIO pins. For analog input data acquisition, rotating the input-output dashboard potentiometer produces a voltage within 0 to 5 volt and passes to the 8-bit ADC circuit. The ADC converts this analog voltage into an 8-bit digital form and sent to the Raspberry Pi Toolkit through the dashboard DV0 to DV7 terminals. According to the equation 1 mentioned before, 19.53 mV ADC resolution was calculated that indicates for each 19.53 mV change in input, the output will alter by 1 unit. The Toolkit controller application transfers this data to the ThinkCentral cloud with the dedicated sensor ID to store and read further from the database table and represent graphically as well as statistically in the web service of ThinkCentral cloud platform. As for the AOTP, dragging the slider of the Toolkit controller application will produce a pulse width modulated signal whose duty cycle is varied according to the slider value. This pulse width modulated signal passed to the input-output dashboard to display generated analog voltage level in a voltmeter. According to equation 2 mentioned before, a 0.033 n step size was calculated, which indicates that change in each slider value will be multiplied by 0.033 and generate voltage within 0 to 3.3 volt. A teaching and learning module was designed once the toolkit has been developed. Contents of this design teaching and learning module are enlisted in the table 4. This teaching and learning module will expose students to the basic knowledge of STEM and IoT through the project-based learning method. Throughout the module, students will be able to learn about various microcontrollers and microcomputers, electronic circuits, operating systems, and programming language. The module also enabled students to have a hands-on learning experience to replicate the experimental outcome shown in this work through the sessions enlisted. The developed system successfully demonstrates a cost-effective IoT solution that enables analog and digital input data acquisition, output production, and storing data in the ThinkCenter cloud platform dedicated database server. With it, students can be exposed to the basics of data acquisition and control from devices, also able to perform visual data analysis, remote monitoring, data processing, and ubiquitous content access for STEM learning through an IoT-based cloud platform. The proposed system can be facilitated as a starting point to teach students on analyzing analog electrical variables like voltage, current, power usage, and managing digital systems like logic gates, smart sensors. A teaching and learning module has been designed, motivated by the potentiality of this toolkit to provide exposure to STEM learning and cultivate interest to acquire IoT knowledge to the younger generations. Based on the performance observations, the proposed system offers a cost-effective cloud-facilitated solution for the project-based learning approach, also exhibits salient suitability to effectively introduce IoT-based STEM knowledge to the students, non-technical personnel, even domain experts at the shortest possible time. The system is tailored for STEM learning purpose at reasonable effort and cost, where the targeted users are the researchers, engineers, and students. This system is currently under investigation by the engineering department students of University Kebangsaan, Malaysia, to support IoT facilitated STEM education in several schools in Selangor, Malaysia. The research team is currently in the progress of implementing the multi-factor authentication and dynamic token scheme to avoid the malicious use of the Think Center platform and potential cyber attacks during the project-based STEM learning sessions. In the future, the implementation will be further enhanced to deal with wide-scale STEM variables from smartphones, microcontrollers, embedded devices, and even from HVAC apparatus as well as home appliances. That's all as of now. Thanks for watching.